In this series, I started with a model of matter in which individual particles are composed of photons of the appropriate energy, making 2 revolutions per wavelength. I have gone from that through the structure of all matter particles and how they unite to give the physical world around us. But no picture of the universe can be considered complete without an understanding of the physics of Einstein's gravity. You may think it is necessary to understand these gravitational field equations and their solution to understand his gravity work. As an example, these equations 47 are Einstein's original equations. On here we have a couple of modernized forms of them, and below is the accepted solution to them. It is my hope that by the end of this presentation, you will understand their physical meaning. In my opinion, Einstein developed his field equations to highlight his theory of gravity being produced by mass distorting 4-dimensional space-time. For that purpose, he used tensors. They are just vectors in more than 3 dimensions. They are not needed to understand the physics behind his theory. Einstein used the differences between his theory and Newton's inverse square law of gravity to calculate his predictions. To understand Einstein's gravity, you need to understand the difference between his calculations and Newton's calculations. In this presentation, I deal with gravity outside matter. That is gravity that holds us to the Earth's surface, holds Earth in orbit around the sun, and holds our sun in its position in our Milky Way. Look, I have to use some mathematics. I've tried to keep it as simple as possible. This presentation is most about the relatively simple physics, so I hope you should not have too much difficulty in following it. The best way to start a study on gravity is the same as everyone else's introduction. It's Newton's inverse square law. This top section describes what is taught at high schools. It explained all gravitational observations for about 200 years after its introduction. Einstein's gravitational work also started with Newton's work. The reference is this paper here. Although his theory was absolute, his calculations were not. They were variations from Newton's work. He gave space-time distortion by mass as the reason for gravity to exist. Einstein commenced his work by determining the effect of Newtonian gravity on photons. So a knowledge of photons is required to understand his gravity. We have a speed c, a frequency nu, energy E equals h nu, wavelength lambda, and mass mp equals h nu over c squared, where h is Planck's constant. Photons with mass are part of Einstein's theory of gravity. They are subject to gravitational attraction, just like everything else. This illustration was redrawn from an English language translation of Einstein's 1911 publication. In it, he calculated the influence of Newton's inverse square law of gravity on photons. This is also where I commenced this study. It should be noted that projectiles are constant mass particles that lose speed as they rise against gravity, whereas photons are constant speed particles that lose mass and hence frequency as they rise against gravity. This diagram shows what happens when photons of kinetic energy E equals h nu move distance delta r against the gravitational field. A photon moving distance delta r from r1 to r2 against mass m, its potential energy, the potential energy is m mass times gravitational field times height becomes h nu over c squared, which is mass times gm over r squared, which is the acceleration due to gravity, times delta r. Conservation of energy means that ke2 equals ke1 plus delta pe. That gives h nu 2 equals h nu 1 times 1 plus gm over c squared times delta r over r squared. Rearranging the terms gives h nu plus delta u nu equals h nu minus gm over c squared times delta r over r squared. Dividing both sides by h and rearranging gives delta nu over nu equals minus gm over c squared delta r over r squared. G, M, and C are constants that can be combined to give alpha equals 2gm over c squared. Substituting that into the earlier equation and setting the limit of delta r tends to 0 gives d nu over nu equals minus alpha dr over 2r squared. Integrating from r1 to r2 gives ln u2 minus ln u1 equals minus alpha over 2r2 plus alpha over 2r1. Or nu2 equals nu1 times e to the alpha over 2r1 minus alpha over 2r2. That shows how much the frequency of photons changes as they move through a gravitational field. Look, all of this is nothing more than early university undergraduate physics and math. That's about as complex as it gets. I'm going to stick with my earlier statement. Know the physics and the mathematics becomes simple. Equation 5 can be applied to the frequency change of photons traveling from the sun's surface to Earth. Alpha for the sun is 2.954 kilometers. The sun's radius is 7 times 10 to the 5th kilometers, and Earth's orbit is 149 million kilometers. Substituting into this equation gives a frequency change of e to the 2.954 over 1.4 million minus 2.954 over 298 million, or 2.1 times 10 to the minus 6. That was the same as reported by Einstein and has been subsequently verified by observation. That means observers in low strength gravity see known oscillations in a strong gravity at a lower frequency. That is why time moves slower in a higher gravitational strength field than in a lower strength field. And that is the cause of time dilation. But that was as far as Einstein went with these calculations. He derived the equation for the bending of light rays by the sun. He missed one factor and only got half the answer. But through the relationship C equals nu lambda, that equation 5 can be rewritten as lambda 2 equals lambda 1 e to the alpha over 2r2 minus alpha over 2r1. When a photon's wavelength is changed, it's called redshift and is denoted by Z. Redshift is the increase of a photon's wavelength. It can be due to the effects of gravity or the Doppler effect. It is given by Z equals lambda r minus lambda naught over lambda naught, where lambda naught is the photon's wavelength at the origin and lambda r is wavelength at distance r from its origin. Equation 7 can be used to calculate the redshift due to the influence of massive objects. Setting lambda 1 equals lambda 0 and lambda 2 equals lambda r gives lambda r equals lambda naught e to the alpha over 2r. That yields z equals e to the alpha over 2r minus 1. When r is much, much greater than alpha, that reduces to z equals alpha over 2r. From then on, simple calculations show that the distortion given by a massive object changes the Newtonian, Euclidean, Galilean, or whatever you want to call it, distance. I've denoted it by as dn. The relativistic distance drel is given by drel equals dn times e to the alpha over 2r. In other words, Einstein's relativistic distance equals the Newtonian distance multiplied by 1 plus z, because I mentioned earlier, e to the alpha over 2r equals 1 plus z. In a similar manner, time distortion by a massive object is given by time at distance r equals time at 0 multiplied by e to the minus alpha over 2r, or trel equals tn e to the minus alpha over r. That reduces to trel equals tn over 1 plus z. That is what Einstein's mass distorting space-time means. Distances and times, as determined under Newtonian mechanics, are multiplied by or divided by 1 plus z respectively to get the relativistic distances and times. It is those relativistic distances and times that are the actual distances and times. Now, those equations were good for determining what happens radially out from the center of mass. They are no good for determining what happens in non-radial travel. For that, it helps to calculate the space-time metric. Oh yeah, it can be done. So Minkowski developed an equation for four-dimensional space-time continuum as s squared equals c squared t squared minus x squared minus y squared minus z squared. From then on, it is a matter of converting that into a differential form that also involves the transfer from Cartesian to polar coordinates. Look, it's been done so many times, it's virtually a standard mathematical lookup formalism. But to help understand it, I will follow the procedure used by Schwarzschild. The Cartesian differential of Minkowski's equation becomes ds squared equals f dt squared minus h times dx squared plus dy squared plus dz squared minus j x dx plus y dy plus z dz, where f, h, and j are functions of r given by r equals the square root of x squared plus y squared plus z squared. Changing this to polar coordinates gives ds squared equals f dt squared minus h plus j r squared times dr squared minus j r squared d theta squared plus sine squared theta d phi squared. The distortions in space-time are measured by variations in the wavelength as given here. It follows from that f equals e to the minus alpha over r, h plus jr squared equals e to the alpha over r, and j equals 1. Now, as I said, I'm just following Schwarzschild, the process he used, but I think you'll find it's quite valid. When you substitute those into this equation, you get ds squared equals dt squared e to the minus alpha over r minus dr squared e to the alpha over r minus r squared d theta squared plus sine squared theta d phi squared. Now, it just so happens that a Maclaurin-Taylor series expansion of e to the minus alpha over r gives 1 minus alpha over r plus alpha squared over r squared factorial 2 minus alpha cubed over r cubed factorial 3, continuing on to minus alpha to the n over r to the n factorial n. When r is much, much greater than alpha, a first approximation of equation 10 becomes ds squared equals dt squared times 1 minus alpha over r minus dr squared over 1 minus alpha over r times r squared, the theta squared plus sine squared theta d phi squared. Equation 11, this equation is one of the accepted Schwarzschild metrics. While that math may look complicated, it's nothing more than a lookup equation in some calculus text. Equations 10 and 11 show that the two approaches are similar. At r much, much greater than alpha, the only regions where they have been experimentally tested, they are indistinguishable. In this derivation, equation 11 is shown to be an approximation to equation 10. General relativity experts refer to equation 10, that's this one, as the weak field, and equation 11 as the strong field solution. If only life was that simple. Here are three more Schwarzschild metrics. The first feature to note is they all have the 1 minus alpha over r term in them. The top two have terms c squared associated with time. The bottom two don't. That is attributed to the normalization of constants. I think that should be known, that's relatively regularly used in mathematical physics. Equation AASM2 is a negative of equation AASM1, and AASM3 is a negative of equation 11. So they refer to travel in opposite directions. No big deal. Well, not quite. As shall be shown later, it appears to have made a huge difference. As an aside, it's an interesting exercise to look at the derivations of those solutions from various formats of Einstein's field equations. Here is an extract from a Stanford University derivation of the Schwarzschild metric. is page after page of this type of mathematics. And do you really want to go through pages like this? Well, I'll tell you what, it's certainly enough to deter your average amateur from proceeding any further. Is it enough to confuse the average professional? You can be the judge of that later. It is now time to have a look at some other predictions Einstein made. This illustration shows a photon gamma passing close to a massive object at distance r0 from its center of mass. Referring to this figure, when a photon is at distance r from its center of mass, it experiences a space-time distortion, delta dist equals z equals alpha over 2r. The total space-time distortion is given by delta dist equals integral from minus infinity to plus infinity of alpha over 2r dr. Since r equals r0 over cos theta, that becomes delta dist equals the integral from minus pi over 2 to plus pi over 2 of alpha cos theta d theta over 2r0, and that equals alpha over r0. With alpha equal 2.954 kilometers and the sun's radius r0 equals 700,000 kilometers, that gives a deflection in radians of 4.22 times 10 to the minus 6. Multiplying that by the number of arc seconds per radian gives a total angular deflection of 0.87 arc seconds. That is also obtained by considering only the potential energy under Newtonian gravity. As the derivation of this equation shows, as long as r is much greater than alpha, there is a time distortion figure, which is the same as the space distortion correction, although of opposite sign. When the two are subtracted, the total distortion becomes 2 alpha over r0, which gives delta S equals 1.74 arc seconds. And photons measured at Earth have not traveled back to infinity with respect to the sun. So this corrects to 1.73 arc seconds when measured from Earth. And those results have been verified by observation and agree with Einstein's predictions. Alpha over 2 r0 is the redshift of photons from the sun's surface to infinity. Transferring that to other masses means the total path distortion in radians of a photon passing a massive object is 4 times the redshift of its distance of closest approach to the center of mass of that massive object. And that's the mathematics of gravitational lensing. That gives enough information for interested parties to determine the amount of mass in a massive galactic structure that causes gravitational lensing. Einstein's gravitational lensing term is double that obtained using Newtonian gravity on the mass of photons. Newtonian mechanics does not include any effect of time distortion. It is time now to look at the precession of Mercury's orbit around the Sun. This diagram shows the redshift the Sun causes at different distances away from its center. Diagram B shows the orbit of Mercury precessing in its direction of travel. Mercury's orbital radius Rm is obtained by multiplying its semi-major axis R0 by 1 minus e squared, where e is its orbital ellipticity. The Sun has distorted distances by the redshift it creates. So Mercury's orbital radius Rm becomes Rm times 1 plus z. That is the extra distance that Mercury has to travel to complete a full cycle from perihelion to perihelion. Having to travel that extra distance means it has to travel a little longer to get back to its perihelion position. That is why Mercury's orbit precesses in its direction of travel. So that the precession is delta circle equals 2 pi rm times 1 plus zm minus 2 pi rm, which is just 2 pi rm times the redshift. Mercury's angular orbital precession, epsilon m per orbit, is given by r times radius times epsilon m equals delta circ, or epsilon m is just 2 pi times the redshift, sun's redshift at its orbit. But Earth is also influenced by the sun. A correction for the sun's redshift must be made to Earth, and that gives epsilon m equals 2 pi times Zm minus Ze, where Ze is the sun's redshift at Earth. Mercury's orbital period is 88 days, giving it 415 orbits per Earth century. During that time, Earth makes 100 orbits. It will only see Mercury making 315 orbits. So as observed on Earth, equation 13 now becomes epsilon m equals 2 pi times Zm minus Ze multiplied by 1 minus m orb over E orb, where m orb and E orb are the orbital periods of Mercury and Earth respectively. In order to solve the precession of Mercury, we need to use these figures. The speed of light, c, Newton's universal gravitational constant, the sun's mass. These values give alpha equals 2.954 kilometers from the sun. Mercury's semi-major axis R naught and Mercury's eccentricity, they combine to give Mercury's redshift equals 2.663 times 10 to the minus 8. Earth's orbital radius gives it a redshift of 0.987 times 10 to the minus 8. Mercury's orbital period and the number of Mercury orbits per century, and of course Earth's orbital period is 365.25 Earth days per year. I've repeated equation 14 here, and it's the calculation for Mercury's precession in radians per orbit, which is a function of Mercury's total orbit when viewed from Earth. To get the precession in arc seconds per century, you must multiply it by the number of Mercury orbits in an Earth century and the number of arc seconds in 360 degrees. And that can be expressed in this equation here. So when the right keys on the calculator are pressed in the right order, you'll get an answer of 42.99 arc seconds per century. That should be compared to Einstein's derivation at the bottom, which the experts tell us gives us 42.98 arc seconds per century. Personally, I would not like to have to make a living off those differences, but some of those who call themselves general relativity practitioners insist this work is wrong. They claim it is a weak field solution. I will leave it up to you to decide which you prefer to use. I see an advantage in this work as offering a physical explanation for the relativistic effects that Einstein calculated. Most people believe his work was derived from purely theoretical considerations, and it largely was. All this work does is show the physics behind the gravity is the effect of mass on the propagation of photons. He used this when he introduced alpha into his solutions. He got alpha from the previous 1911 study I referred you to. So knowing the physics, we can extend some calculations in other directions. Many people believe that Einstein's equation for precession of Mercury's perihelion applies to all observers. This derivation and equation suggests that observers in different locations will get different results. The general equation for Mercury's precession as measured from elsewhere becomes epsilon m equals 2 pi times Zm minus Zo times 1 minus m orb over O orb, where Zo is the redshift caused by the sun at the observer's orbit and O orb is its orbital period. This table shows that observers in different locations would get different answers for their observations. Those are the values per 100 Earth years. Features to note are that an observer from beyond the solar system would see Mercury's anomalous orbit at almost 90 arc seconds per 100 Earth years. Observers accelerated in a retrograde Earth orbit and held in place by a large solar sail would see Mercury's anomalous orbit at about 56.63 arcseconds per century. But Einstein's theories are called relativity because measurements made by observers in different locations give different results. His theories enable people to calculate the results expected to be seen by different observers when the speed of light was constant for all observers. The general equation for the precession of a satellite orbiting the Sun as measured from Earth becomes solar naught equals, I'll leave you to read that out. It's really, this term is just the redshift at the satellite's orbit, and the rest is straightforward. And RS is its semi-major axis of the satellite, and S orbit is its orbital period. I mean, basically, as I said, these are just redshifts. The general expression for the precession in arcseconds per orbit of any object about any mass m external to the solar system is given by epsilon equals 2 pi times 2gm over 2c squared times 1 minus e squared r naught. These terms have the usual value, and that's of course multiplied by 1.296 times 10 to the 6. And that's just 2 pi times the redshift at the body's corrected radius multiplied by 1.29 times 10 to the 6. Now is a good time to have a closer look at the predictions of Mercury's orbit. Mercury's measured orbital precession is 5,600 arcseconds per century. Newtonian mechanics predicts 5,557 of those. Earth's equinox gyrates to 360 degrees every 26,000 years, so that gives 5,026 of those arcseconds. The gravitational pull of the other planets, mainly Venus, Mercury, and Jupiter, is 532.2, so that the difference, what's called the anomalous precession, is 43 arcseconds per century, and that was what was predicted by Einstein, and you've just seen its derivation anyway. Look, Einstein did not calculate Mercury's orbit from scratch and find out that it differed from Newton's work by 43 arcseconds per century. He predicted the extra. Now, so his work was really a modification to Newton's work of about 2.6 times 10 to the minus 8. So Einstein's calculations complement Newton's work. They do not replace it. Newton also predicted that all planets would prescribe an ellipse as they traveled around the sun. If gravity was less than inverse square, it would precess in the direction of travel. And as I explained earlier, the reason for that is quite simple, that when gravity is weaker than inverse square, it travels a little bit further away. It has a little bit further to travel to get back to it, to go from perihelion position to perihelion position. It precesses. But if gravity is stronger than inverse square, then the sun pulls the planet in a little closer. It will have less distance to travel to get back to perihelion position, and its orbit will regress in its opposite to the direction of travel. Now, that was predicted by Newton in his Proposition 45, Volume 1 of his Principia, which was first published in 1687. Basically, the last time I checked, Mercury's perihelion was precessing in its direction of travel. So here's where it starts to get interesting. Other papers, of which this one is a reference, have derived Mercury's orbital precession using one of these accepted forms, or actually using this accepted form. The calculated result was a precession of 42.98 arcseconds per century. The interesting feature is that it is calculating in the opposite direction. In other words, the calculation is for motion in the reverse direction. That appears to indicate that the author has predicted a precession in the opposite direction. In my language, that equates to predicting a regressing orbit. So does the complexity of the mass mean that it was not picked up? I'll leave that for you to work out. It's now time to have a look at aspects of Einstein's derivation. Oh, just before you do that, here's a book that I have got. You'll see it's well thumbed, well bent. It's been read a lot. First feature to note is that his work involves approximations. I mean, he says so. In this top highlighted section, you'll see there is only a minimum of arbitrariness. That is not the same as this is an exact solution. He only uses tensors of low rank and only second order derivatives. He didn't have to be more accurate. He was only considering small variations from Newton's predictions. The second highlighted section shows his approximations were good. I mean, his first approximation was Newton's law. His second approximation was the motion of the perihelion of Mercury. He was quite right to point out the correctness of the theory. It works well within the approximations he used. He also used other approximations. This one starts out with G11 equals minus 1 plus alpha over R. Remember this equation here. It follows from this equation that dx equals minus 1 over 1 plus alpha over 2r. But this extract shows that he went on to say that dx equals 1 minus alpha over 2r. That is correct to a first order of small quantities. Well, when alpha over r or alpha over 2r are small, there's not much difference between 1 over 1 and its inverse. So he went on to say that the unit measuring rod thus appears a little shortened. That may seem to be a contradiction to my earlier statements that a strong gravitational field causes length to increase. However, you should look at the words that followed. The unit measuring rod thus appears a little shortened in relation to the system of coordinates by the presence of the gravitational field. The gravitational field increases the length of the coordinates by alpha over 2r, which is indeed z, as I had shown you earlier. So viewed against that stretched background, the unit measuring rod will appear a little shortened. And it is a little shortened by, it will appear shortened by 1, well, the change dx is 1 minus z. But the results obtained in this redshift approach and Einstein's approach are the same. The difference between Einstein's work and this redshift work is the difference between e to the alpha over 2r minus 1 and alpha over 2r. They're indistinguishable when r is much, much greater than alpha. Those who want to say there is something wrong with Einstein's derivations are partially correct. He used approximations, not exact derivations. Within the realm of his approximations, I find no error. However, I will admit to one problem. His mathematics seems so complex that most people appear unable to follow or understand it. And I would like to suggest that includes most specialists. But there are large differences in other aspects of redshift work and the further progress made, supposedly based on Einstein's field equation. His gravitational field equations have been transformed, and this is a modern Ricci tensor form. But irrespective of that, the accepted solution to Einstein's field equations involves the term 1 minus alpha over r. It is shown here in this exact solution. Look, I accept that it is an exact solution to one interpretation of Einstein's field equations. However, an exact solution to an approximation is still an approximation. One of Einstein's approximations was that correct to a small order of magnitudes, 1 minus alpha over r equals 1 over 1 plus alpha over r. It works well for r much, much greater than alpha. So really this accepted solution is only applies for r much, much greater than alpha. as distinct from this redshift metric, which is an exact solution and I think applies for all R over alpha. This slide shows the three theories describing gravitational attraction. Newtonian gravity, denoted by Gn, is just Gm over R squared. There is no redshift in Newtonian mechanics. That means that by default, Newton's work treated photons as either traveling at infinite speed or having no mass. But don't be too harsh on him. Photons weren't known for over 200 years after he published his work. Allowing that photons have mass and travel at a finite speed, Newtonian mechanics gives this redshift metric. I was mentioning earlier that Newtonian distances become relativistic distances 1 plus z times r. So if we substitute, if you put that into Newton's equations, you get these expressions for the acceleration due to gravity and the gravitational force. Now, but because 1 plus z equals e to the alpha over 2r, when that's squared, you get this term that the acceleration due to gravity is gm times r squared e to the alpha over r. The accepted metrics, referred to as Schwarzschild metrics, are approximations that are only valid for r much, much greater than alpha. Getting an exact expression for these terms becomes difficult. Probably a nice word of saying it's not really possible. So if we change the denominator from r to 1 minus z, you get these terms. And then that gives, the problem with that is that when you substitute z by alpha over r, you get this term, 1 minus alpha over 2r squared. However, the accepted Schwarzschild metric shown below, everybody expects a singularity at r equals alpha. So to keep those people happy, I will use this acceleration for gravity term of gm over 1 minus alpha over r times r squared. Like, it really doesn't matter what term you use. It's an approximation that has no validity in Einstein's work away from r much greater than alpha. This slide summarizes the acceleration due to gravity under the different theories. The gravitational redshift theory operates on the distance from the center of mass, and the denominator is r squared e to the alpha over r. Newtonian mechanics also operates from the center of mass, and its denominator is just r squared. The accepted Schwarzschild metric, I will use the denominator as 1 minus alpha over r times r squared. It shows that gravity acts through the Schwarzschild radius. I mean, that's what black hole practitioners believe, so we might as well use it. The main feature of these illustrations and equations is they can be used to calculate the acceleration due to gravity under the different theories at different distances from a massive object. This slide shows the calculated relative acceleration due to gravity for these different values of r over alpha. This redshift metric refers to accelerations due to gravity under the redshift metric. In all of these cases, to get from this value to the actual accelerations, you have to multiply by big Gm. This column refers to Newtonian mechanics, and this refers to the Schwarzschild metric. Not surprisingly, gravity under it goes to infinity at r equals alpha. It's just called the strong field solution to Einstein's field equation. As I said earlier, it is based on approximations and has no physics to support it. In my opinion, it is easier to understand the differences if they are plotted out, which is shown here. The redshift metric is in red, Newtonian mechanics green, and the Schwarzschild metric is in purple. A quick glance shows that the redshift metric is always weaker than the Newtonian gravity, and the Schwarzschild gravity is always stronger than Newtonian gravity. They all trend to the same value as r gets much greater than alpha. At r equals 5 alpha and smaller, they start to digress quite significantly. The Schwarzschild and Newtonian equations results in gravity extending to infinity. Schwarzschild metrics get there at r equals alpha, and Newtonian mechanics gets there at r equals 0. The acceleration due to gravity associated with a redshift metric increases to a maximum at 0.5 alpha, and then goes back, diminishes to 0 at the center of mass. To quote one mathematician, that is what the mathematics tells us, so it must be right. But that is not the way things work. Physically, it means that mass is so great that its space-time distortion dominates the inverse square law. The mathematics given by the e to the alpha over r term supports that idea. It may seem a surprising result, but consider the thought experiment shown here. An observer at O in A is surrounded by concentric rings of uniform density that extend as far as required. According to Newton's shell theorem, the observer will not experience any gravitational force from the surrounding mass. There is no limit on Newton's shell theorem. Einstein's gravitational field equations do not override Newton's work. As the mass is progressively compressed through B and C, the observer will still not experience any gravitational field. When the mass is compressed to a point D, will gravity at its center suddenly become infinite? Under Newtonian mechanics, the answer is yes. Under the Schwarzschild metric, it will become infinite in r equals alpha. Under this redshift metric, the answer is no. Look, nature abhors singularities. There is no singularity in this redshift metric. Think of it this way. With an equal amount of mass in all directions, say at the center of an object like the sun, there will not be any gravity. It may, like a sun center, have huge pressure, but it won't have a gravitational field. Besides, it's an academic consideration. No matter how great is the mass, it cannot be compressed to or collapsed to a point singularity. However, that equation does indicate that the gravitational field on a massive object may not be as strong as expected close to it. This slide shows a two-dimensional representation of the three-dimensional strengths of the different gravity fields generated by this massive object at the center of the diagram. It was obtained by rotating the earlier equations through 180 degrees in both axes. My opinion is these diagrams are easier to understand than these equations that are used, these field equations that are used by others. So don't be too impressed by people who talk about gravitational field equations. It's a complex way of saying that acceleration due to gravity at different points in space away from a massive object. But many high school students could calculate the Newtonian gravity, which are these, could calculate these curves. The other two metrics you see are slight variations from that. So my recommendation, look, just forget the complex mathematics. All that is needed is these equations, the redshift, Newtonian, and Schwarzschild, if you wish to use it. All you need is those equations and the parameters you want, like the mass and its distance, and a good pocket calculator. Put the required values into the appropriate equations, press the right keys in the right order, we'll get the answer. I'm going to go so far, if the answer is not the same as those obtained by field equations, there is an error in the field equations. Yeah. But if you want to use these curves to determine the acceleration due to gravity at any point covered by them, it is necessary to know the mass of the gravitational attracting body. From that, you calculate its Schwarzschild radius. Then you select the distance you want, divide it by the Schwarzschild radius alpha, and locate it wherever it is on this curve. Then you just extend back to this point here and multiply by gm to get the strength of the gravitational attraction at that point. These curves show that at r equals 10 alpha, there is not much of a difference between the gravity under the different theories. A central body with a mass of billions of suns will exert one all hell of an attraction over huge distances. For that sort of mass, by the time an object reaches a distance of 5 alpha over r from its center, which is reaches about here, it makes almost no difference as to which theory you use to calculate the particle's incoming speed. It is the gravitational attraction over huge distances that gives the attracted particles such high speeds that relativistic corrections must be made. This slide shows just the redshift metric. Gravitational attraction under the influence of the massive blackbody's origin is again greatest here at r equals 0.5 alpha. This does require that the object is so massive that a Schwarzschild radius alpha is outside its physical radius. So think gravitational attraction, think of particles rolling along a sloping surface with an incline, an upward incline at the end. Particles will tend to gather in the region of greatest gravitational attraction, which is here. And by the time particles attracted by billions of solar masses have reached this distance, they'll have relativistic speeds and masses. Particles don't move in radially. Collisions, friction, and general interference between those relativistic particles would concentrate around r equals 0.5 alpha. At relativistic speeds, they will get hot, very hot, as they swirl and move around, colliding with each other in the massive object's accretion disks. These colored regions are meant to indicate a slice through a torus or donut-shaped accretion disk in 2 dimensions. The brighter the color, the stronger the radiation emitted. This colored shape is supposed to be a torus sliced in half. If matter was coming in from a planar galaxy disk, it would be expected to form a torus in the galactic plane. When viewed from a distance, it would look something like this. It will be a bright torus ring centered around r equals 0.5 alpha and on a less bright center and background. Massive structures containing billions of solar masses don't just appear from nowhere. They accrete mass over ages. It's actually quite an interesting exercise to calculate how such a structure would grow. If the particulate matter came in from 3 directions, as in a globular cluster, that shape would be represented by this torus rotated through 180 degrees. The brightest signal will still come from the edges, no matter from which direction it was viewed. In the above, I've shown that the idea of black holes originating from Einstein's field equations is a fanciful mathematical extension of approximate equations to well beyond the realms of their applicability. In other words, I'm saying they don't exist. Against that are these Event Horizon Telescope collaboration images. They are said to be black holes surrounded by an energetic accretion disk. They were taken from galaxy M87, which is a globular galaxy estimated to have a mass of 5 to 7 billion solar masses. And this Earth is the galaxy shown here. The bright rings in these structures are purported to be images of the accretion disk with the black hole in the center. These white circles represent the resolution limit. The images are a great achievement. They show what can be done by international cooperation. But I'd suggest they're a long way from proving that the structure represents a black hole. This slide shows the image from the previous redshift metric with the torus reduced to approximately the same dimensions. I mean, it should be pointed out that a 10 billion solar mass object at a galactic center would have a Schwarzschild radius of about 3 times 10 to the 10 kilometers. A distance of r equals 10 alpha is about a 3% of a light year. Over a distance of 55 million light years, that requires measurements to be accurate to better than 2 parts in a billion to have any possibility of distinguishing between 2 metrics, which at that stage differ by less than 15%. Then again, the predicted mass depends upon the metric used. For the same observation, the redshift metric will predict a higher mass than the Schwarzschild metric. It is suggested that other possibilities be explored before the object is officially recognized as a black hole. I mean, the predicted shape under this redshift metric bears a very close resemblance to the observed shape. At least the redshift metric torus has a physical basis. The difference of a factor of 2 over 55 million light years using a metric that will underpredict the mass. I suggest that the explanation for these is much closer to the map from a black hole. I was going to use this diagram to illustrate many absurd features about black holes. It illustrates a situation of gravitational fields in a body with a mass of 3 billion solar masses. With all the properties ascribed to black holes, it requires gravity to act from a hollow sphere of thickness much less than a nanometer at a distance of 10 to the 10th kilometers from its center of mass. I mean, there is no physics behind black holes. They are a mathematical solution to distorted approximations taken to distance well away from their applicable region of the approximation. But Einstein never believed they existed. Just hope you can understand he was right. And I'm suggesting that Einstein was not wrong. It is all the others who are wrong. Look, it's time for a quick refresher course on precessing orbits. These diameters are a reminder that orbital precessions require gravity to be weaker than inverse square. The reason is simple. Weaker gravity means that an orbiting body travels further away from the attracting mass. It has to travel a greater distance to complete its orbit. Its perihelion will precess in its direction of travel. If gravity is stronger than inverse square, the body orbits closer to the massive object. It doesn't have as far to travel to complete an orbit. Its perihelion will regress. I mean, that is the end of the story as far as the physics is concerned. Newtonian mechanics predicts Mercury's orbit almost from scratch. Einstein's relativity was a correction of about 2.6 times 10 to the minus 8. Is it feasible that a variation of less than 3 times 10 to the minus 8 was going to totally reverse a physical principle? I don't think so. I mean, physically proving otherwise would make rather interesting viewing. The last time I checked, the orbits of Mercury and star S2 were both precessing in the same direction as their orbit. That requires a weak field solution. The concept of gravity being stronger than inverse law, Thales Physics Lesson 45, first published in 1687. The perihelions of Mercury and star S2 precess. Gravity being stronger than inverse square also fails Einstein's equations in his foundations of the general theory of relativity. That's this, which I have here, and from which those approximations and everything was taken. Yes, I've studied it well. No matter how or why the misunderstanding developed, it should not reflect on Einstein's work. Now, he was brilliant. I'm not questioning his work. Mind you, it would be interesting to have an explanation from black hole practitioners as to why exact solutions to approximations are an exact result. However, for those who would like to be an amateur gravity sleuth but can't follow Einstein's gravity field equations, the following is offered. Use this illustration of star S2 orbiting its massive body. You can use that to determine the precession per orbit. The website at the bottom gives some information about it. Then just use this equation to check out its mass or other properties. It is not that difficult. When it comes to black holes, the choice is a simple one. There are 3 gravitational theories. Newton's inverse square law of gravity allows a singularity at r equals alpha. It does not allow any change in its orbital status and does not predict black holes. Schwarzschild metric is a strong field solution. It allows for a singularity at r equals alpha. However, it only allows for an orbit to regress. and it does allow for black holes. This redshift metric produces what's called a weak field solution because it's weaker than Newtonian theory. It does not allow a singularity, but it does allow for an orbit to precess, and it does not allow black holes. Look, it is mathematically possible to derive Mercury's precession from one of the approximations Einstein used in deriving his field equation. I mean, after all, he did it. It is possible to mathematically derive the Schwarzschild metric from another interpretation of his approximations. After all, that has been done. But it is not possible to have both physical effects in the same approximation. You can have either black holes or orbital precession. The two are mutually physically exclusive. Now we come to the question that if there's nothing wrong with Einstein's gravity field equations within the approximations he used, how did those who follow get his work so wrong? This is going to be a bit technical, but it's the only way I can explain it. In my opinion, these three equations show why. The first feature to note is these two field equations do not contain the term alpha. So what? Well, they had to get alpha from somewhere. This Ricci tensor format has the term G mu nu. That refers to what are called G11, 12, 13, 14, and all the way through, and it's shown here. The terms 1, 2, and 3 apply to the dimensions x, y, and z, and term 4 applies to time t, as shown here. Look, they may look complex, but in a radially symmetric situation, the only coefficients of concern are G11 and G44. Radial symmetry just means it is either falling under gravity towards or moving upward away from the center of mass with no sideways movement. Einstein derived G11 equals -1 plus alpha over r. From that, he derived G44 equals 1 over 1 plus alpha over r. I mean, it has to be because G11 and G44 are the negative inverse of each other. But in his paper, he expressed that to a first approximation, G44 equals 1 minus alpha over r. When alpha over r is about 10 to the minus 8, that is a very valid approximation. In the solution to the field equations, the alpha's origins are hidden within the complex mathematics. I have no intentions of going through them. Instead, I will point out how those terms and approximations played out. For G11, Einstein derived this term. You saw it earlier in one of the slides I showed you. In his equation 71, he went on to express a derivative as dx equals 1 minus alpha over 2r. And you can see here that basically comes here. When r is much, much greater than alpha, that is an approximation to the square root of that. When that term is squared to get back to G11, it becomes this term. 1 over 1 minus alpha over r. The Schwarzschild metric uses this term. Einstein derived G44 equals 1 over 1 plus alpha over r. He wrote it in his paper as the approximation 1 minus alpha over r, which of course, again, when it's alpha over r is the order of 10 to the minus 8, it is very valid. So this is picked up in this equation here. And that is what is used in the Schwarzschild accepted Schwarzschild. These are what are used in the accepted Schwarzschild metrics. Had those who followed his work used what Einstein derived in his paper, they would have come up with this metric of ds squared equals dt squared over 1 plus alpha over r minus dr squared times 1 plus alpha over r minus r squared times theta squared plus sine squared theta to phi squared. It supports all his other predictions, including Mercury's anomalous orbital precession. It does not support black holes. Einstein never believed in him, and the equation 1 over 1 plus alpha over r is also a good approximation to e to the minus alpha over r. The experts got it wrong when they picked these approximations instead of what Einstein derived. And I hope that makes it easy to understand why Einstein did not believe in black holes. In this study, I did not mention Einstein's brilliant idea of being at rest in gravity or accelerating in gravity-free space are indistinguishable, and conversely, free falling in gravity was the same as being in gravity-free space. And I believe this in principle was incorporated into his field equations. But the physics behind Einstein's gravity is that mass distorts space-time. Space is measured by the wavelength of photons. Time is measured by their frequency. Photons have mass and are therefore affected by gravity. Space and time distortion is changes to the wavelength and frequency of photons respectively. Both are determined by the redshift of photons. Mass increases length by 1 plus z and slows down time by 1 over 1 plus z. Where the effects of redshift are not detectable, Newtonian mechanics calculations will match observation. Where they are detectable, relativistic mechanics must be used. Now that provides a link between Newtonian gravity and Einstein's relativistic gravity. Newton's inverse square law can and was used to determine changes in the wavelength and frequency. Einstein introduced approximation when he derived his field equations. The Schwarzschild solutions to his equations used two sets of approximations from his work to predict the existence of black holes. They have no physical or sound mathematical foundation in Einstein's work. Because of the approximations he introduced, Einstein's equations were good for distances of r much, much greater than alpha. He determined the redshift z equals alpha over 2r. This study has led to a new redshift metric that derived z equals e to the alpha over 2r minus 1. The Event Horizon Telescope images appear to confirm that it applies to all alpha over r. Look, I'd just like to go a little bit through the understanding of gravity. I think you all know Nicholas Copernicus suggested that the sun was the center of motion. Tycho Brahe made detailed studies of the motion of planets over many decades. Johannes Kepler put some order into Brahe's findings. He and Galileo Galilei established the heliocentric model of the solar system. Newton, using some of Kepler's results, introduced the inverse square of law of gravity. He showed that gravity applied to everything on Earth, as well as the motion of the planets around the sun. He also showed that orbital precession was possible if gravity was weaker than inverse square. Newton's laws successfully predicted every gravitational observation for almost 200 years. But then again, Newton had no idea what caused gravity. Einstein indicated that gravity was caused by mass distorting space-time. He showed it was possible for gravity to be weaker than inverse square and correctly predicted Mercury's anomalous orbital precession. He also correctly predicted gravitational lensing, the redshift of photons, and others. His work made a minor but observable and significant difference to Newton's predictions. Einstein's great contribution to gravity was to explain its origins. After his death, general relativity practitioners misinterpreted his calculations, suggesting that gravity could be stronger than inverse square and predicting massive objects could form black holes. In doing so, they seemed unaware that orbital precession is not physically possible when gravity is stronger than inverse square. It is either that or they derived their own values which have nothing to do with Einstein's work. This redshift metric study shows that applying Newton's inverse square law to photons gives rise to Einstein's predictions. It predicts the shape of the detected by the Event Horizon Telescope, which was attributed to black holes. All of that makes no difference in the results predicted by Einstein in the world around us. outside our world, it makes the universe of difference, as it shows that there are major interpretational difficulties associated with many established theories of the universe. Newton's work was a great leap forward in understanding gravity. He took it from a great puzzle to a relatively well-ordered study. He had no idea how it worked. Einstein solved that puzzle when he indicated mass-distorted space-time to produce gravity. He determined the effect of small space-time distortions beyond Newtonian gravity. Einstein did not indicate how space-time was distorted. This study has explained that Einstein's gravity is mass changing the wavelength and frequency of photons, and it also extended to large distortions up to r less than alpha. As I see it, there are two major gravitational studies left: how it plays out in the large-scale structure of the universe, and what are the properties of space-time that mass distorts to produce gravity. When you know that, you'll get the answer to why gravity is so weak. Have you worked it out yet? Mathematicians and theoretical cosmologists with tales of black holes have fascinated the public since about 1960. Gravity stronger than the inverse square is not physically possible, nor can it be accurately derived from Einstein's gravitational field equations or this redshift metric. Black hole proponents should not say they were mathematical solutions derived from Einstein's field equations. If they do, it shows they did not understand his work. And as that famous and highly respected physicist and mathematician John Williamson told me, if there is an error in the mathematics, it is usually in the second equation. That holds true for black hole mathematicians. Their first equation starts out with some version of Einstein's field equations. Their second equation does not correct for Einstein's approximations. However, if people want to show that black holes exist, they should, first of all, show physically why Newton's derivation of gravity being weaker than the inverse square could not lead to orbital precession, while gravity stronger than the inverse square does lead to it. They should show why Einstein's derivations were exact when he said, and I have shown, they were approximations. They should independently derive the G mu nu terms, particularly G11 and G44, and describe the physics that supports them. They should then fit them into a space-time metric, and then finally show the physics of how gravity can be concentrated into a large spherical shell of radius 10 to the 10th kilometers with a thickness of less than 1 nanometer. Well, that was a brief introduction to the physics of Einstein's gravity. I hope you enjoyed it. I will now leave you with some of the topics I can cover later. Thank you for your attention.